Okay. In this week. So, as you see, we're done with these second and third week's chapters. Now we will try to understand what are the number systems. Actually, in our first week, we talked about this matter a little bit. Now we will see some more details about these number systems. In here, actually, we have four basic number systems. As you see, decimal, binary, octal, and hexadecimal. So we have a general, and we actually are so familiar with decimal number system. As you know, we are using the decimal number system in our daily life. But in computer language, we should know this binary language because it understands just ones and zeros. As you know, we should convert our decimal numbers, octal numbers, and hexadecimal numbers to these binary numbers. And actually, for these decimal numbers, as you know, we have an ASCII table to convert some characters into some numerical characters. Actually, for example, if you press uppercase A button from your keyboard, actually it is 65 as a number in the background. And this 65 number is a decimal number. But you should teach this number to your computer as a binary. You should convert this binary 65 number to the binary number. Because this device understands just zeros and ones. Number systems, decimal number system, binary number system, and actually just differences are base number. For our decimal number, the primary number system, our base is 10, as you see. But computer knows base 2. And octal number system, base 8, and for hexadecimal number system, base is 2. Actually, we are using this number system. For example, especially hexadecimal number system, base 16. We can see the number system in image processing, for example. Or if you are creating any website, you can encounter these numbers in color codes, for example. You may see some characters which are represented by letters, uppercase, lowercase letters. It can be maximum F, for example, and F represents 50 in this hexadecimal number system. And octal number system, how can we encounter in our daily life as a programmer? For example, inside the processing system, you may encounter. So, to apply these operations, you should care these octal number systems. And what is a bit? It's just a bit. It's just a one character, as you know. Stands for a binary digit with a single place or focus in a binary number. Can be a 0 or 2. Yes. And so as you see, we have non-binary number system example as well on the right side. So we have not this explanation, but at the rightmost side, actually, we have a least significant bit at the right side, and the most significant bit is at the left side, as you see. So, for this binary number is called as nibble. If you are using 2 nibbles or 8 bits, so we are calling this as bytes. And then if you are using 2 bytes, so we are calling it. And then if you are using 2 words, so these are some types. And for our real lives, actually, we are so familiar because we can encounter with some memory issues, memory problems in our cell phones, in our cloud accounts, right? So if you have some memory problems, you should pay some money, for example, to get some much more memory area, right? So actually, at the basic area, we are buying so many bits. Okay, so these larger version of these bits actually, so 8 bits can called as bytes, and then we know gigabytes, terabytes, right? So if you want to buy any hard disk, you are carrying actually terabyte or gigabyte size, right? So it's so familiar with us. In general, while the decimal number systems is used in most areas, binary and hexadecimal number systems are used in digital electronics and therefore in the processor and microcontroller. Actually, if you have an electronic device, we are using this binary system in the background of the system, right? So in expressing quantities differently, numbers consisting of digits according to a certain number, the base are used. So our examples, we have an example as you see is in base 10, as you see 158. So if you don't see any information about this right bottom side, it means again that is a number in base 10. It's a decimal. But if you are writing any binary number, you require a bottom side. So it's a binary number, our base is. And at the right side, you can see so these are equal with the base 10 number. So it's this number, the binary version of this decimal number. And if you want to calculate this hexadecimal version of this binary or decimal number, so you will see this kind of number. So we will see some letters instead of these numbers, right? So actually, these are again the number in the vector. For example, this E is a 40. And at this octal version, as you see, now our base is 8, but here is in this, we are showing this number in this base 8. Okay. So we will see some conversions between these number systems. So number system and our numbers. So in this binary number system, our base will be 2. And here we can use 0. It cannot be allowed to take 2 or more like now. So we have just 2, 5. And then in here, for base 8 of the number system. So here as we are starting with 0 and highest number can be 7. We have 8 characters to show our number in the base 8. And base 10, in order base 10, and here, we have some characters, we have 10 characters, we are at this 10, base 10. And the highest one can be 9. Okay. And also for 16, there's a decimal number system. In this one, as you see, we are starting again with 0. And after 9, how can we show this path? By using just one character. So now we need to use these letters. So A actually is 10, B is 11, C 12. Sorry, 12. 10, 11, 12, 13, 14, and 15. So it can be maximum 50. F is not 60, it's 50. Okay. Is there any question till here? Right. So, how can we express our decimal numbers? We can calculate this value of the number. If you want to write the open version of this number, you can use this approach. As you know, we all know this way. And because we know we are using the base 10 now, real life in here. So the power of this 10, I want to write on this slide. So initially, you should write these numbers. It will be some power numbers for this calculation. Now, we will carry the values for these digits, okay? And in this digits, as you see, so 4 times, we are writing this one. Our base is 10, and we are writing the 0 according to this situation, okay? And then, for the next one, initially, we are writing this value of this digit. So, multiplying with this one, so the power is coming from this order, okay? And we are adding these values to calculate the exact value, okay? So actually we know this calculation. Actually, I just want to remind this one because we will use the similar approach for other base. Okay? For example, if you want to calculate for octal system or hexadecimal system, you will apply the similar steps again and again. And the concept of an analog, digital, and binary number systems. And all information is an uninterrupted, continuously variable flow is analog. So analog and digital structures, actually we can encounter with these terms for some device definitions. For example, if you have a machine, if you are playing with some analog signals, we are carrying this uninterrupted and continuously signals. But in our digital devices, we should care these interrupted signals. So if you have, it is just an electronic device, as you know. So it uses electricity, right? And then actually it is using this 5 voltage. So we are actually carrying this energy as one. If you have no energy at that pin, we are actually assuming we have no power at that pin, and we can assume this pin's value as 0. We have some processors, as you know, and these processors have so many pins on them, as you know. And these pins are working with this logic in the background. If you have the energy, if you have the power at that pin, yes, we can assume this part's value as 1. If you have no power, we are assuming this value as 0. And decimal system, binary system. Actually, we will convert our numbers with each other. Initially, for example, in decimal system, our base is 10. In binary system, our base is 2. For example, I want to convert this 0, so 0, 0, 0. We have no more part. So 1 equals this one. And in this part, actually, we used 5 bits, as you see, because in this table, we are converting this number at the right side. So you don't need to some more bits at the left side. If you want, you may put some more zeros at the left side. Okay. So, for example, in this one, I want to show briefly in here 0, 1, 2. These are powers, by the way, and 3 and 4. So it means actually our base is 2. So we will, if you see any 1, 2, and then so in this part, as you see, actually we have 1 at that digit, 1 times and plus. Do you have any signal at this digit area? No. you don't need to care this one because it will return 0. So we have 1 at that part. So in this, it means plus, we will multiply, and then we won't care this other parts because these are zeros. And we will calculate the sum of them. 16 plus 4 equals 20. Okay, so by this way, actually, you can convert these numbers between each other. So, most significant digits, MSD. So the leftmost bit called as actually MSD, and the rightmost bit called as LSD, least significant digit. Okay, in this part we will care our floating numbers. So this part actually, and it is a decimal number. So we know these decimal numbers, and how can we express actually in this part? So we're done with this left part of this point. We can write in this way because the power of this 10 is 0, 1, and 2. So here is the calculation, the open written part. And then how can we write this right part? So now this time our power will be -1 for 5, -2 for 6. And then we are adding these numbers by this way. Okay? Actually, you all know this calculation. We are just remembering. And I will skip this one. Binary numbers. Actually, in this binary numbers, we can create these floating numbers in this way here. Again, the MSD is the left side, and the right side is our LSD bit. And how can we convert our binary number to a decimal number? In this part, we will see this. So, actually, just a second, because writing in this zoomed version, it's impossible. Start. So initially, you should write these powers or order numbers onto the lower side of them. And here, it's a binary number, and we will find this decimal version of this number. How? Let's see this. 1, 0, 1, 0, 0, 1, 2, and 3. Actually, our value of this digit is 0, and what is the base? Is 2. So what is the power? 0 for this one. Okay, and then plus. So we will write for this digit, and here is the base and power plus. Then we will see for third digit, 0 times base is 2 and the power is 2 plus 1 times. So as you see, we are calculating this structure's result. Okay, and then you will see 0 for this, and then 2 for this, 0, and 8. When you add these numbers between each other, you will get 10 as a binary number. Sorry, decimal number. Okay. Do you have any question in this part? Okay. Mm-hmm. 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 Yes. Yes, yes, you may use some more digits. At the time, your power to may encounter, for example, this one is 60. You may see 22, 64, because these are. If you understand this structure, actually, we will repeat the similar structures for other number systems. So, another example for this conversion, actually, calculating the conversion result, and then by adding this result, we can find easily its decimal versions of this number. Again, I try to put some more examples to you, but if you want to solve on your own, actually it can be much more better because learning at the time much more possible. Listening is not enough for these calculations. You should actually solve this kind of questions on your own. Okay, I try to put some answers and questions to you, but I put some more exercises. They have no answers in the slide. And in this part, let's solve again. I'm writing over here. I'm writing powers again, the top side of this one. So as you see, we have 6 digits now, and our base value is 2. It means it's a binary number. So for the first one, as you see here is the calculation. The power of 2 is 5 now. Then we are calculating this structure's result. We are calculating actually digit by digit in here, and after the summation, we will get this decimal number as a result. Okay. And in this part, we have another binary number, but it's a floating number, as you see. Now we will write again 0, 1, 2, and 3. But for the right side, you should write -1 and -2, just like our decimal numbers. Okay. And then we're done with this left side, but for the right side, our base is 2 now, as you see. And then our result is 0 for this, but for this one, it will get, as you see, this number. And by adding these values again, you can get this result. Is there any question? No? Great. So actually in this part, we can see another example. We have no floating number in here, as you see. And if you care this structure, actually in this binary calculations, our base is always 2. Just the difference is this. The other parts are the same, actually. What about this signed and unsigned number types? Actually, if you are if you are writing any code, we have some data types, and these data types can be in these 2 types. For example, if you are defining any number, you should declare a type for this number, and this number can have a sign or not. For example, if you are calculating any counters result, so you don't need to define any signed type, right? Because this counter cannot be a negative number at that scenario. So at that case, you can use this unsigned version types for these variables. But in here, we are assigning this left bit and actually MSP bit as a time. So get for this number area, and for now, this MSP can be assigned as a sign with in this sign version, sign numbers. Okay, so this number values are defining actually our sign structure. It can be a negative number, it can be a positive number. So it depends on this MSP's value. In the binary number system, the leftmost bit, 5-bit MSP is used as a sign bit of the number. Okay. For example, as shown below, how the number it can be obtained in an unsigned 8-bit number is 255 because we have 8 bits to create our binary number. But if this decimal value can be the most 255 because we have 8 bits. But if you are using this prime number, you have 7 bits. Because we are using this MSC as a time bit in that scenario. So as you see in this part, if all of these bits are 1 in this 8 bits, you will get this result as a decimal value. In this scenario, you're losing this MSP bit. So, and this is quite important in the price volume in this order. But we are assigning this bit as a sign bit. So it can be find this positivity or negativity scenario. So at that case, if you have 8 bits, so you will get maximum this. And now, in this part, as you see, if you find this as 1, so actually it means if you see this kind of version, so you will see minus 147. Okay, so if you find this 1, the number is negative. If 0, this number will be positive. So if you see this kind of declaration, it means it's a positive 127. These are boundary values. You cannot define 128. So it's not enough value. Okay. And these are some exercises for your, okay? And you should follow and you should actually try to solve these questions from your own answer. What you do, you don't need them, solve it, solve them. That's all. Okay. But as I see, you have no problem for this calculation. Right? Am I right? Do you need some more examples? Great. Because we are repeating the same process for some other numbers. And in here, how can we convert our decimal number system to binary number system? Where's my? Actually, we have some milestones today. Binary to decimal. So we're done with this step now. Now we will see conversion decimal to binary. And base is 2, base is 10, base is 10, base is 2. Okay, so we're done with this. So how can we convert this structure? So as you see, we have a division process in here. If you want to, this process continues until the result is less than 2, because our base is 2, as you know. In this part, as you see, we have a decimal number, 22, and we will divide this number by 2 because our base is in this binary system. Okay, so we will continue, remain is 0. Then by 2, 5, 1, 2, so now this result is less than 2. We can stop at that point. Then we will write by starting by this result in this way. So initially we will write this result in this first area. Then for this remaining value, then we will write this one, then we will write this one, and finally we are at this. So here is the binary number for this question. Okay. So the direction is so important, and for some scenarios you can forget this first area. You should share this volume. You should share this without any problem. Okay. You should start with this result, and then you will add this remaining values in this order. Okay. So by this way, we can convert our numbers to a binary. And we have some other approach to calculate this version. For example, for 50, if you don't want to apply this division process, you can try to find the highest two part. For example, I want to, for 8 this, I will write and I know this number 5, 6, and 7. So this one equals 5 and 7. So it means actually this 50 in this part. Actually, we have 42 for this. Do you have any 64 in the 50? No. So you don't need to care for the left side. I want to find some volume from this side. So what is the top part? Now we will try to create some parts. For example, if is equal to power 4, right? And then, so it means actually this one, right? So in this part, actually, you don't need to put, but if you want, you can write for 5, 4, 3, 2, 1, and 0. We have no digits for this part without so 5 and middle one for it. We have no digit for this, but you can use this digit as 1. And for this, you have 16, yes. And you have this power, no. We have this one, no. We have this power, yes. Part 1 and 0. So you may remove this left side. So it is from 1, 0, 1, 0. Okay. Actually, I don't prefer the second way. This one is much stronger and faster, I think. No, if you encounter with this kind of question, actually we can inform you about the sign operation. If it is a sign structure, you should allocate this one as a sign bit or the other bit. And then digits can be at the left side. This one can be sign bit. Okay? But in our general usage, actually we are using our unsigned structure for our calculation. But it's just an information for you. If you have any signed number, we are using the MSB bit for this declaration, for this actually signed specification. But we are actually generally applying these conversions for our on-site. We are not carrying the sign structure, generally. Let's see this one. Let's repeat. Our decimal number is 45. We will divide by 2, 22, and then main is 1. Main is 2. And then by 2 again, 5 is 1. Divide by 2 again, remain is 1. Last step, 1, and then 0. So we will write by starting with this result. Initially, you should put this result module in here. And then here is direction for this bits. 0, 1, 1, 0, and 1. Here is the result. Okay. Do you have any question? Direction is so important for this convergence. If you write in this way, you will get the wrong result. But if you're lucky, you will get the correct result. And it's the second approach. These are some more conversions. So binary conversions for fraction numbers. If you have some floating numbers, how can we convert? Now we are in the decimal area. So for this left side, actually, for the integer part, we are again applying the same process, just like this one. But how can we convert that to right part? Actually, you're removing that block on that side, and you're getting this right away. Then you're multiplying this volume by 2 because we want to identify so after this calculation, we will get this result. So we will get the changing part. Then we will multiply the right again. This multiplication process for 3 or 4 times, it can be don't need to calculate answers. In here, actually, we are getting this part again. So we get this part, everyone. Then we multiply the right part by 2 again here. And also, you don't need to multiply this by 2. So it will get 0 if you try again and again. So you don't need to write more zeros and left. Because our significance level actually decreases to the right side, just like our decimal number. In this part, for example, what is the significance level? Actually, for 2 points. 1, 3, 9, 3, 4, 5, blah, blah, blah. So we can write a rounded version of this value, right? You don't need to sum more digits at the right side because these are not important for us. You can write briefly 1, 3, 9. That's enough. You may remove, you may create some rounded values. Okay, just like into this decimal version, if you calculated this 3 digits for the right side, actually that can be enough. Okay, so in this part, and also if you are creating your own examples for exercise, in this part we have some online converters. You may add your numbers, you may specify your, for example, from decimal to the line, here specifying this conversion, and then we are entering our decimal number. I will use this homework, you can get the result. And you can check the result for it by using this kind of platform. Okay, this link is for this one. And for this, let's try to write. So we have a number and we want to get binary number of this part. Initially, we are multiplying this number by 2 because our base is 2. So here is the integer number. We are writing this part and then we are getting this part to calculate second step. So we are multiplying by 2 again. Now our left part is 0. Then we multiply this number again by 2. Okay. Then we will get this one. So we have two parts for this coding numbers, as you see. By writing this way, actually, we can write this number. So in this part, first one, and the second one, and the third one. Okay. Do you have any question? Or no? All right. And some more examples for you. First one, as you see, we have some numbers, and these are not clouding numbers in here. As you see, in this part, you will find some binary versions of these numbers. If you have any question for this binary and decimal number systems, you may ask, by the way, because we will start to see this octal number system. Okay. The 8-digit number system is widely used in digital electronic systems, sound and music applications. And you may encounter in these markets if you are a programmer, if you are a coder, actually. And also you may be a project manager and you should know some details for this project. For example, in this project, you can encounter with some failures and with some errors. You should understand what is the error. You should create some solutions as a project manager. If you have no idea, possibly you won't be a project manager anymore in the future at this scenario. And in this part, just like our other number systems, we have an MSD bit at the left side and LSD bit at the right side. And how can we calculate? Actually, just like our decimal part, in this part, actually, I want to convert this number to a decimal number. Let's see this example. Our number is 4753. It's an octal system. And we want to find this decimal number. So the difference is just base value, because now we are in this octal number system, right? So actually our powers, again, 0, 1, 2, and 3. For first one, for first digit, now we're multiplying our digit value by this value, 3 times 8, and then plus, get this digit value, and then multiply with this, okay? We are repeating the same process by using different base numbers. In this part, so this number is an octal number system. We will try to find this decimal version of this number. In this part, as you see, for 4, so the power is 1, we know. For 7, the power will be 0. So now we will use this base number as 8 again by adding these numbers we will get 39. Now we are forwarding octal to decimal. So it's an octal number system. 0, 1, 2 are colors. So for this digit, it is going to be this one, the multiply with. And I added the plus digits for you. You are getting 50 and we will see. It is just related with this octal decimal. Okay. Again, octal decimal application. In this example, it is the power of 6 is minus 1, as you know. So after this part, we are adding so minus 1 power for this plus. Okay. A similar process is repeating again and again. Oh, so other part, decimal to octal. So base is 8, base is 10, base is 10, we will convert this number to base 8. How can we do it? By dividing. Okay, now we will divide our decimal number by 8, calculate this octal version of this. Just like this one, actually calculate the binary number, we are dividing by 2 because our base is 2. Now our base will be 8, so we should divide by 8 in this scenario. Just like this one. Now we will get this octal version of this. Now we are in this octal number system. So what is the remaining value? The main value is 0, 7. I see. And then division result is this one. And then we'll continue by dividing 8. And the results, sorry. Am I right? Yes. From this part, again, we can write this part again. 3, 6, 7. Okay. So actually, in this part, they are showing this structure in this way, but in the background, we are calculating this equation. Okay. Do you have any questions? If you want to convert any decimal number to any number system, you should carry the base with you. So we will see the similar step for base 60 for hexadecimal number system. And again, we will apply the similar structure again. So in this part, we're going to check side of the point. Here, actually, this is the difficult digit because was written as 3. Actually, it's not important because it's the LSD bit. In this part, let's see, I want to show this one. So the upper side represents is the left side of this number. So So we know how can we convert this one, right? So we can write 2 in this order. You should write 3 and 1. So we're done with this. So as you see, for the result, we're done with this left area. So how can we convert this right part? Our base is 8. You should multiply with 8. Okay. So in this previous version of this, we multiplied by 2 because our base was 2, as you know. Now we will multiply this value by 8 in this case, as you see. And you will get the right area of the comma. Then we will multiply this value by 8 again by this way. So we will write this left value, left side of this comma to this area. So here we will repeat the same process again. We will multiply this value by 8 again. Then we will write this value in this part. So at the right side, as you see, we will write 4, 0, 6, 5, and 1. Okay, so it's the octal version of this decimal number.
In octal to decimal conversion, we multiply by 8 numbers from the category for the other, like behind the column, the numbers behind the column, we divide by 8. Let's say this 22.25.
Decimal. Actually, in decimal, at the left part of this comma, you should divide by 8. But at the right side of this comma, you should multiply by 8. In this scenario, we are multiplying, actually we are calculating this structure. We have no multiplication and we have no division operation. We are converting this octal number to a decimal number. So you should apply this approach. Okay, so for all of these conversions to base 10, you should use this approach. But if you are converting your decimal number to any other base, so you should use this approach. Okay, and if it is a floating number, if you have some fractions, so you should carry this left side and right side separately. Okay, left side must be divided by 8 or 16 or 2 again and again. It depends for your number system. And if you want to calculate the right side of this number, so it means you should multiply. Actually, we have some actually different structures because we have different directions. We are multiplying and we are dividing, right? So we will see again, actually, in this hexadecimal number system again. And this one, binary octal conversion. Binary to octal. Now, try to assume we have a binary number. Our base is 2. We will find this octal version of this number. How can we do this? Actually, if you remember hardly this approach, you can convert this binary number initially to decimal, and you can convert this decimal number to octal version. It's a longer way, as you know, but we have a short way here. And for example, 10112. And after this, I will give a break. 1011. So it's a binary number. We want to find octal version. This definition says when converting binary numbers to octal numbers, the binary number is divided into groups of 3 from right to left. So we will create 3 members groups from right to left and right to left. If you have no member at the right side, you may add 0. Then we have 2 groups in here, as you see. And if you calculate this one's result, so actually, how can we calculate? 0, 1, 2. So I'm writing this open version. 1 times plus. So the result is 6, right? It means you have 6 in this cell. In this group, so we have, I'm writing directly 2 and 4, so it means, so we have 2. You may merge 2 numbers with each other here, octal version of this number. Okay, so this conversion is so actually easy for implementation. We have 3 members in the cells. Why? Because the power of our base is 8, right? In this octal number system. So power of this number is 3. So you should put 3 members for each group. Okay. The reason all this group count. Okay, member count. Do you have any question for this one? Let's have a break. After the break, we will continue for this conversion.